That's the simplest one, and the observation is, as I said, observation is a single sample. Whenever I take a simple random sample, I denote my observations by little x1, little x2, little x3, little xn. So consider selecting two different samples of size n from the same population distribution. Then the xi's in the second sample will virtually always differ at least a bit from those in the first sample, right? Okay, if I go out and collect soil samples, I get 10 soil samples, and I'm looking for lead. I collect 10. On day 1, I get the average, and I go back out the next day, collect 10 more, I get the average of those. You think the averages are going to be equal?
No.
No. Okay?
Or
They always
should.
differ. Once in a great while, they may be the same, but
Don't count on it.
the probability is 0 that they'll be the same, depending how many decimal places you get out. Okay. All right, so they always differ, and that's due to basically things like that are usually not constant in life, right? They just vary from where you are. Nature has natural variability to it. It has small scale variability and it has large scale variability. It has both. And then we have measurement error too. So there's all sorts of forms of error getting into your estimates. Now here's something from real life. Okay? I had this question asked to me by somebody up on this site. Okay? Well, you have the tanks filled with all that nuclear waste, right? And what they have is, and they want to vent all the hydrogen gas all the time. So they have these fans in there, constantly sucking out air from the tank and running it through a filter. Okay. So what they have, so they had two airflow meters. Okay. They had two airflow meters. So they had one airflow 1, and they had these measurements from it, and then they had airflow 2. And they had these measurements from it, and here's the time that they took them. Okay, you can see there's sort of, this one doesn't have as many observations as the other one, and they miss sometimes due to anything. But in airflow 1, so they ask me these questions. They say, are they the same or different? And then they ask me, is one more accurate than the other, and which one should we use? Now that sounds like reasonable questions to ask a statistician, doesn't it? Doesn't that sound like reasonable questions that a statistician could answer, right? I mean, obviously, are they the same or different, right? So you can look at them. I plotted them over time, and there were the measurements. And if you just look at it, what would you conclude?
Airflow 1 is,
Huh?
I would think Airflow 1 is more accurate.
Well, airflow 1 looks like it's higher than airflow 2, right? In general, maybe not. They're sort of, when you get up in this range, it's not, but it seems.
In a few spots, it seems like they're different.
It seems like it's lower, right? It could possibly be lower. And if I said that the airflow 1 is greater than airflow 2, you may not. I could do actual. So this is something where you want to do a statistical test to see whether the mean is different from one to the other, right? Because they were sort of close together at points, and you go, well, they sort of look like they might be different, but we better do a statistical test to do it. And then they asked me, okay, is one more accurate than the other?
Realistically, you couldn't answer that because it doesn't.
Why can't you answer that?
Smaller standard
You don't know the
deviation
actual
means
values.
more accurate than-
You don't know what it is, right? You don't know which one is. How do I measure accuracy here? I don't know what truth is, right?
You can say one's more precise than the other.
I can say one's more precise than the other. I can say which one has a smaller variability, right? But
Yeah.
I can't say which one's closer to the truth, okay?
Yeah.
Because I don't know what the gold standard is. I mean, who knows what it is? These are questions people will ask me. Then they ask me which one should you use. So, since I don't know what truth is,
Can't give you an answer.
yeah, so the only thing I could answer was this one. But I mean, these are legitimate questions people will ask you, but you have to figure out what you can answer and what you can't answer. Just because you have some data doesn't mean you can give somebody an answer to what they want to know. So don't get deluded in that thing. More things have gone wrong by people trying to stretch what the information has and trying to say something than, I mean, this happens all the time, right? So anyway, it happens all the time in politics. You take little factoids and stretch them into things that are totally unbelievable. But anyway, that have very little scientific merit. But anyway, I don't know what to say. I'm not shut up on that. Anyway, so you got to be careful. You're using statistics. You see things. You have to know what you can determine and what you can't determine, and it's useful. Okay, so statistics. The value of a sample mean from any particular sample can be regarded as a point estimate, right? Why do we call it a point estimate? Because basically we're taking our data and reducing it to a pointer, right? A point estimate. An average is a point estimate. It gives you one number, and it's a point. Okay? If I estimate a variance, it's a number, so it's a point. Okay, so those are point estimates. Okay, so the values of individual sample observations vary from sample to sample. So in general, the value of any quantity computed from sample data varies, and that's something we have to be interested in. Okay, so if I estimate a mean from this lead sample thing, I go out and take 2 samples of lead. I take 10 lead samples from around the campus, and I take it. Next day, I take 10 more, so I get 2 different numbers. I guess if I did it for a whole week and did 7, I did it 7 times. I took 70 samples, 10 days a week. I'd have 7 different numbers. Correct? So what does that mean? I mean, okay, so I go, okay, now I have 7 different means. And I scratch my head and I go, well, what is the real mean, right? Who knows? Who knows? So that's something we're going to work towards. Statistics is any quantity whose value can be calculated from sample data. Okay? Prior to obtaining data, there is uncertainty as to what value of any particular statistic will result, right? We haven't collected any data yet. There's uncertainty in what we're going to see. Therefore, a statistic is a random variable and will be noted by an uppercase letter. So if I just go out and get one observation, it's X, right? If I go out and get a sample average, it's going to be X bar, right? If I go out and get a sample variance, it's sigma squared. I get the sample standard deviation, it's S, capital S. And lowercase letters, X bar, S squared, S, Xi is used to represent the calculated statistic or an observed value of the random variable X, okay? So the capital ones are the unknown point estimate, and these are these lowercase ones as the actual calculated values. Okay? That's the difference between uppercase and lowercase in statistics. You see lowercase letters, they're actual calculated values, and you see uppercase letters, it's just saying it's a random variable. And so if I'm looking at the random variable X bar, if I'm looking at X bar, I go out and then I'll calculate this one, which is little X bar, right? Okay, so yeah, a lot of this probability distribution of any particular statistic depends not only on the population distribution, whether it's normal, uniform, binomial, or wherever it came from, and the sample size n, but also on the method of sampling. Okay? So you got to be careful when you take samples. Consider selecting a sample of size n equal 2 from a population of just 3 values, 1, 5, and 10. And suppose the statistic of interest is the sample variance. If sampling is done with replacement, then S squared could possibly equal 0. Right? So if I take 2 samples from 1, 5, 10, and I sample with replacement, that means I take one sample out, look at it, throw it back in, take another sample out, I could get the same one back again, correct? So I could get 5 twice. If I tried, so I have 5 and 5, I calculate a variance for that. There's no variability in the data, so the variance is going to be equal to 0. So that's a possibility, right? However, if I did it without replacement, that means I take out a 1 and I hold on to it and take another one, then I'll always get a variance. Okay. So you got to be careful how you sample. Okay. Whenever I'm saying I'm taking a simple random sample of size n, okay, now here's the thing with the soil thing. Now I got to sample soil. Can I sample soil with replacement? Can you sample the sugar and grapes with replacement? Some things you can sample with a replacement, some things you can't. If I can't, once I take an aliquot of soil with lead in it and I throw it in a GCMS and I vaporize it and see what I got, I can't go back and put it back, can I? So some things you can sample with replacement, some you can't. So you got to be careful what it all means.
But you could sample a grape from the same plant, or you could have a sample from that same.
Yeah, but you can't get the same grape, so you can never put anything back, right? It's the same thing as soil. It's done. You can assume that something next to it is the same characteristic, but you never know.
That's true.
I guarantee you, sample 2 grapes from the same cluster, you'll probably still get 2 different sugar contents if you have enough decimals. Yeah. So okay, it's just the way the world works. Anyway, you look at a cluster of grapes, you may have one little dried out one on it, and one that's really plump and juicy, and if you take the little dried out one, that's what you're going to catch.
Really high.
Yeah, it'll be really high, right? Yeah. So anyway, what can I say? You never know. You never know what's going to happen. That's what I told you before. You have to plan your experiments carefully, right? It's like playing a game of Monopoly. If you think you're going to if you think you're going to run into sampling problems, you better take care of the case, because if you roll your dice and it falls off the board, whether you're going to count it or not. Okay? Whenever you sample things, take into mind all the problems you can run into. If you're going to do a real big sample, it's always best to practice on a small sample. If you're going to spend lots and lots of money to take samples, it's best to go out and first do a small study, find out what problems you're going to have collecting data, and before you go out and spend a lot of money collecting a lot of data. So you're always going to find out you're going to collect something you didn't expect. I guarantee it. Ready? So before you plan big studies and start taking sampling, do it. The thing you can do is, what we're going to assume, whenever we do anything in this course, I'm going to assume that we're sampling with replacement, and if you have enough data, and if your population is infinite, like if I was sampling lead from the campus here, and taking little aliquots of lead, it's like I'm taking a little jar of lead from the campus, so I say I have a little vial, and I'm collecting soil in it. How many little vials, about that big, do you think I'll have for the first foot of this whole campus? A few billion, right? Probably a few billion. So I can assume that I'm sampling without replacement. That I'm sampling without replacement, basically. Okay. So I mean, if n is big enough, if the big N is big enough, and it all depends on the ratio of n to n. But sometimes you really don't know what big N is. But you have to think that out. But what we're going to assume is that the XI's are a simple random sample. That means they're been sampled with replacement. The XI's are independent of each other. That means that one sample has nothing to do. The taking of one sample does not affect the taking of another sample. They're not related. And if every XI has the same probability distribution, right? I'm saying they're all coming from the same population, whatever that might be. It's random, it has variability, but it's coming from the same population. If not, if some of those are violated, then we have to think of a different way to sample, and that's a different course. Okay, that'll be under sampling theory. Random samples. Probability rules to be used to obtain the distribution of the statistic, provided that it's fairly simple. Functions of the xi's are either, I don't know. Okay, for our course, for what I'm going to do here, I'm going to assume things are either binomial for this course, or they're normal, or they're coming from a normal population. And if I don't come from that, if I have time, I'll show you how to deal with that. There are lots and lots of ways to deal with things that are not normal, but that's another couple of courses worth of work. So I'll show you, if I have time, I'll show you some easy ways to deal with data when it's not normal. Okay? Actually, there's what you do is you simulate with the data, or you can use non-parametric methods, which are really just a finite form of a simulation. Okay, where do I want to go? Okay, this is an important one to remember. This is really important to remember. You don't have to understand the math here so much outside of the results, right? What did I tell you before? That from everything we did before, you have to remember this, and then you're going to learn this, and then if something's normal, we have this, and then we're going to estimate things that way. So you have to know how to compute a mean, you have to know how to compute a variance, and you're also going to have to remember this, that the mean, the expectation of the mean, whenever I take my sample average, no matter what the distribution it comes from, so long as they're all coming from the same distribution, the expectation of the mean is always equal to the mean of the population, right? The variance of the mean is equal to the population and expectation on average. The variance of the mean is the population variance divided by the square root of n. Now, individual observations still have a variance of sigma, right? But now what I'm doing is if I take an average, what am I doing? I think I did this once before. When you take an average, I have 10 numbers, right? So if I have 10 numbers, what am I doing? I have 10 numbers from a distribution that, say, has a mean of, what did I write these before, I wonder? Say I have 10 numbers. So I have 10 numbers, x1, x10, and say they come from a normal distribution. So it looks like that. So I get my 10 numbers, x1 and x2, etc. I have x10 out here. Now I take their average. Where's the average? Roughly speaking. Sort of in here somewhere, right? So x bar is going to be somewhere in there. I take another 10 samples. So this is so sigma here is how spread out each individual is from each other. Now if I take another average, say I take another sample of 10, where's that mean going to fall? Somewhere close to this one, right, in general. So it's going to be, so if I take another sample, x bar might be over here. If I take a third sample, it might sort of be in there. If I keep taking samples, what I'm going to do is they're all going to be, the samples are always going to be pulled in. They aren't going to be near this thing unless I get some really unlucky sample, right? So what happens is, now, so the means are always pulled in. So basically they're going to be, the distribution on means is always going to be smaller than the distribution on the total population. And in fact, it's equal to the total, depending on the sample size, so long as all the means come from the same sample size, the sample variability of the mean is sigma over the square root of n. So what we're doing is just pulling numbers in to the center all the time.
So it's saying if you took a bunch of samples, got a bunch of it's a bunch of sets of samples, calculated the mean for each set, the variance of those means.
Yeah, okay, here it is. I go out, 7 days in the week, I take 10 samples of soil, and I take 10 samples, I measure the lead concentration. So day 1, I get a sample, I get an average. Day 2, I get an average. Day 3, I get an average. So at the end of 7 days, I take 10 samples. How many total samples do I have? 70, right? So I can get a variance for the whole population from all 70 together, right? And now I can also, what's the variance of each one of the averages? So now I have 7 averages, and I can get the average, I get the variance of just the averages themselves, and that's going to be smaller than the total population, because each one of those is pulled in to the center.
Do you need it drawn out?
See what's happening there?
Okay.
I'm taking the 7 numbers, making them into a point, which is closer to the center than any of the numbers themselves, right? And I did that 7 times, so the variability of the average is going to be smaller than the variability of all 70 together. That's all you're really saying. Okay, so if I can get an average, in addition, if I let T equal, okay, so if I want to get, the total amount of lead in 10 samples, I could just add up the lead concentration in each of the, well, I wouldn't add up the concentrations. What I do is I could add up the well, then I would do something else. If I get a concentration, then I'd have to turn it into a mass though. But if I want to get the total lead, it's I can add up each of the individual observations, and the estimation, the expectation of the total then is just n times whatever the expectation of the mean is, right? And the variance of the total is, the variance of the total is just n sigma squared, okay? And so this standard deviation is the square root of n sigma. So this you have to remember. This and this and this are things you just have to remember, okay? Alrighty. If I want to get the total amount of lead, then I have to make some corrections, right? Then I have to account for, if I'm getting a concentration, then I have to account for mass and density of certain things in order to get total lead. But it's just a different calculation. And okay, in a notch tensile strength fatigue test on titanium on a titanium specimen, the expected number of cycles with first acoustic emission used to indicate track initiation is mu is equal to 28,000, and the standard deviation of the number of cycles is sigma is equal to 5,000. Let x1 to x25 be a random sample of size 25, or x is the number of cycles on a different randomly selected specimen, and the expected value of the sample mean number of cycles until the first emission is the expectation is equal to 28,000, and the expected total number of cycles for the 25 specimens is E of t is equal to n mu, which is equal to 700,000. So the standard deviation, x bar, or the standard error of the mean of and total, or so the standard deviation of the mean without even collecting any data. If I know what mu is and I know what sigma is, all these calculations are easy, right? We're still in probability theory now, and what I'm telling you is I know what the standard deviation is, so I just told it to you up there, and I told you what mu was, so these calculations are easy. I just follow the formulas I just gave you. If the sample size increases to n equals 100 instead of 25, then E of x is unchanged, but the variance, or the standard deviation of x bar, now becomes, instead of 25, it's 100, correct? So it's been 100 would be 10, that would be 5, so it's actually been halved. Okay? So if I quadruple the sample size, then I can half the standard deviation. Okay? Which is important. So you can use that as a general rule of thumb. If if I want to decrease, if I have a sample of data and I get this large variance, then I almost have to quadruple my sample size in order to get the standard deviation on the mean to be half of what it currently is, right? So when you're taking samples and things like that in the future, this will come into play when we're doing hypothesis testing, things like that, which is coming up very soon. Okay. Where do I want to go with this? Case of the normal distribution, let x1 through xn be a random sample from a normal distribution with mean, mu, and standard deviation sigma squared. So again, I know what mu and sigma are, so we're back in the world of probability theory. Then for any x bar, and then x bar is normally distributed with mean, mu, and standard deviation sigma over the square root of n, as is t, but t has a mean of n mu and a standard deviation of square root of n times sigma, right? So what I told you on the previous slide was for any distribution. This is in particular for the normal distribution. Okay? We know everything there is to know about x bar and t distribution when the population distribution is normal. In particular, we always know what the probabilities of x bar between a and b are. And if I give you sigma squared, and I can obtain all those things. So the distribution when n is equal to 10 is going to be tighter than it is when x is equal to 4. Why is that? Why is the distribution when I have 10 samples on the mean going to be tighter than it is when I have a smaller sample? Because the variance is equal to sigma squared over n, right? So if I take more samples, sigma squared over n is smaller than it is when
You only have 4.
So when I have 10 samples, the variance is going to be tighter than when it is when I have 4 samples, right? So I have 4 samples, the variance is going to be bigger for the mean. Not the underlying population itself, but the mean. The time it takes to randomly select a rat of a certain subspecies to find its way through a maze is normally distributed random variable. Mean of 1.5, standard deviation of 0.35 minutes. Suppose 5 rats are selected, denote their times in the maze. Let xi's, let the xi's be a random sample from this normal distribution. What's the probability that the total time of the 5 rats for the 5 is between 6 and 8 minutes? By proposition, the total has a normal distribution of mu t is equal to n mu, which is 7.5 minutes, and the variance is equal to n sigma squared. So it's basically 5 times 0.125, right? So it's equal to 0.6125. So then sigma total is 0.783. To standardize T naught, we can, if I want to standardize it, now T naught is still normally distributed. So the thing I can do is I can subtract it, and I can standardize it to find out what the probability is between 6 and 8. Or I could just use, this is the way you do it mathematically. The only thing I could do if I had a standard normal table, or the only thing I could calculate. If I gave you that information, you should be able to use R to do it with a, it wouldn't be between 6 and 8, but if I ask you some other values, you can calculate that with R. So whenever I standardize something, you usually do it when you don't have your computer with you. Determination of the probability that the sample average time, x bar, is at most 2 minutes, requires that mu of x is equal to 1.5. And so the variance is equal to sigma over the square root of n, which is equal to 0.35 over the square root of 5, which so that's equal to 0.565. So the probability of that is equal to, it's going to be 20 minus 1.5 over the standard deviation of that. And so it's equal to 0.993. Okay. Or I could have just calculated it to be, or I could just say P norm is, well, here I just wanted it less than 2. Is it was 2 requires this? I could have just calculated directly. How would I calculate this directly just using R? Forget this part. I don't have to standardize it. I have all the information. How can I calculate that it's less than 2? The thing I do is I just go, okay. I know that X bar is distributed normal. What did I say the mean was then? The mean's going to be unchanged. It's going to be 1.5, right? Mean's 1.5 and the standard deviation is 0.1565. So I want the probability that X is less than, that X bar is less than, what did I say, 2? 2.0? So that's equal to P norm. 1.5, oops, would be 2, 1.5, 0.1565. I don't have to go through all of this. All right.
Can you explain again what T naught is?
That's the total.
That's just the
The total time for all 5 rats. Total time for all 5 rats. So I could be interested in the total time for all 5 rats, or I could be interested in the average for all 5 rats. Or I could be interested in the proportion of rats that are under a certain time. That becomes a different problem. Okay, the central limit theorem. I talked to you about it before. Let x1 to xn be a random sample from a distribution with a mean mu and a variance sigma squared. Then if n is sufficiently large, x bar, so the sample average, has approximately a normal distribution with mean equal to mu and a standard deviation on the mean is equal to sigma squared over n. Okay, so what's underlying all of this is that I know what mu and sigma are. Okay? This is probability theory again. And what I'm saying is no matter what the distribution comes from, I talked about this the first day or something, I said I'd get back to it. So no matter where the distribution comes from, I don't care whether it's really skewed or not, if I take enough data and I know what mu is and I know what the underlying variance is, then I can always say that X bar is normally distributed with a mean mu and a variance sigma squared over n. Okay? But n has to be large enough depending how skewed the data is. So what does large enough mean? I think I had a better graph somewhere else in another one. But, if you take enough data, if this is the population distribution, original population distribution here, looks like that. So for small to moderate n, the mean may still be skewed, but if I take a large number of n's, the mean will always be normally distributed. Okay? This is a nice theorem to know, but it's often misused. Okay? It's misused often than it's ever really used. So, I mean, you can use it, and you can just look at this slide and you can figure things out. I don't want to go through this one. You can use it, not use it. It depends. The book states, well, I don't know. I gave you a different book this time. Usually the book states the rules of thumb is if n is greater than 30, that means if you take more than 30 samples, the central limit theorem can be used. Well, I don't know. However, if you use this without sufficient understanding of the process underlying the data you collected, you'll be wrong much more often than you are right. If the underlying distribution is highly skewed, you need many more than 30 observations. Okay? So, and whenever I wouldn't invoke the central limit theorem unless you talk to someone who knew a lot more about statistics than you're going to gain from this course. Okay? Okay, so the thing I advise you to do is don't use the central limit theorem unless I tell you to do it. Okay, because it's a tricky thing to do. You can do it in your work, but that's going to just give you a rough answer. I mean, if you're in your work and you can get, if you have work and you have data, you want to assume your mean is normally distributed. Say you have a lot of data, you can calculate the mean. Well, you're going to get an answer whether it's correct or not using normality or a t-distribution, which I'll show you later, is going to be questionable. But at least you'll have an idea of where you are. Okay, that is what I should say. So invoke it so you can at least start your work. Okay, and then talk with somebody and to see whether you can actually really use it. Okay. Another thing, anyone hear of a log normal distribution in their work? Anyone hear of a log normal distribution? Well, basically, you take logs of your data. If you take the natural log of all your observations, and they look normal, then what you have is something called a log normal distribution. That's why it's called log normal. You take a log of your observations, and now they're, and if they look normal, and I'll tell you, not today, but another day, I'll give you some ideas of how you can visually see if something's normal or not. Okay. Now we get back to this all comes back to what I was talking about before. This is really where a collection of n random variables and that, so we got distributions of things. This is where everything comes from. So if I let y be the average, then we can see that. We can look at all this stuff, and we get so this is nothing other than the mean, which is equal to that, which is 1 over n equal total. That's x bar really in reality, if you look at things like that. An average is nothing other than a linear combination, except the AIs are just 1 over n. And we can always get things for linear combinations of things. What do I want to say here? So if I have any linear combination of things, you use this sometimes when you have different random variables. Say x1 you're measuring one thing, x2 you're measuring another thing, then the mean of them added together, so long as they're independent, is equal to that. And I take the variance of the sum of things. The variance of a sum, if everything is independent, that means one has nothing to do with the other, is equal to a squared. It's the sum of the variance times whatever the scale factors are. So if a1 through an is equal to 1, what's the variance of the sum of random variables? It's equal to the sum of the variances of each of the individual ones. If the AIs are not equal to 1, then it's going to be either depending on what the value of AI is, I'm either increasing the variance or decreasing the variance, depending whether AI is greater than 1 or less than 1. The standard deviation is the square root of it. For any AIs, if they're not independent, it's going to be equal to the sum of the covariances. I'm not going to talk about the covariance until we get to regression. Okay? So you can forget about that till we get there. I'll talk about covariances and correlation when we get to regression. So what do I do with all this? A gas station sells 3 grades of gasoline, regular, extra, and super. They're priced at $3, $3.20, and $3.40 per gallon. And X1, X2 denote the amounts of these grades purchased in gallons on a particular day. Suppose the XIs are independent, and mu1 is equal to 1,000, mu2 is 500, mu3 is equal to 300. So, and sigma 1 is equal to 100, sigma 2 is equal to 80, sigma 3 is equal to 50. Then the revenue from sales it's $3 times whatever I sell, how many gallons of X1 I sell, $3.2 for however many gallons of X2 that I sell, and 3.4 times X3. So the expectation of that thing is $5,620, and the variance is equal to the sum of the variances times the costs. And so I can expect to get $5,620 a day with a variance of $429, with a standard deviation of $429. Okay, so when you're doing different things like that, it's good to know the linear combinations of things. All right, if they're independent, I can just take the sum of them and get that, and the variance of the sum, and the variance of the sum is the sum of the variances. And we get that information, which would give us a pretty good idea on various costs. So if you're running a computer lab, you're running an operation in a winery, and you want to figure out your cost for something, and you have several different operations going, thing you can do, so long as they aren't correlated with each other, you can go, okay, if on an average day, this is what we do, and this is how much it costs us. If you have functions like that, then you can figure out your total costs for your operation within a certain thing by looking at it that way. You can say, here's the mean cost per day, but I know it varies by that much day to day. So you can get some idea of what's going on in your facility, and you have a better idea that when you see numbers changing, that you can go, oh, that's expected, that it's, say it's 5,600 today and it's 6,000 tomorrow, you go, oh, well, it varies, I have that much variability, and so that seems reasonable, right? I'm going to see that pretty often. Alrighty, so it's good to know when you're looking at numbers how variable they are, and that's all we're really doing. Okay? So when we start looking at sums and averages, we want to know how variable they are. Okay. Now, if I look at differences, this is a funny one. If I look at the difference between two things, then the difference that on average, if I have the difference between two random variables, x1 and x2, then an expectation, I can take the expectation of the first one minus the expectation of the second one, which is the mean of the two. However, the variance of a difference is still the sum of the variances, the same as the variance of a sum. Variance of a difference is equal to the variance of the sum. It's the sum of the variances of the two. Okay? What I'm saying, so there's just as much variability in x1 plus x2 as there is in x1 minus x2. That's all you're really saying there. Does that make any sense?
Yeah.
Okay. Okay, so here's an example of that. You can read through it. So basically just do the calculations here, what I just showed you for the difference, and you can see that if I added them together, I'd still wind up with the, oh, what did I do here? Oh, what did I do here? I made a mistake, didn't I? That should be a plus sign. Right? And this should be ooh, ho, ho, what should that be? Oh, it's going to let me do here. That look better? Okay. That's how that one should work out. Yeah, so if I relabeled these things, if I relabeled them, so the x1 refers to the four-cylinder car, then what I'd get is I'd still get that, and then it would equal plus 4, then it would equal plus 4, but the variance is still no different, it's 3.69. Okay? So, where can I go from that? When everything's normal, it's really no different. The thing we do is we do the same operations, everything's hunky-dory, and we can just continue on the same way we did for that gas station example. We can get that, except now, if I know it's normal, when I know it's normal, now I can start giving you probabilities. Before, all I could say, if I didn't tell you what the underlying distribution was, all you could tell me was what the mean and variance were. You couldn't give me any probabilities because you didn't know what the underlying distribution was, right? But if I tell you what the distribution is, in addition to the information I had before on the gas prices, then I can come up with the probability that the total income from the gas station it's greater than $4,500 is equal to 0.9955, okay? So, information is important. If I just tell you it comes from a distribution, okay, if I tell you a sample comes from a distribution, and I'm not telling you what the distribution is, then you can go, okay, well, I can estimate the mean and I can estimate the variance of that underlying distribution, but that's as far as I can go, okay? I can't make any probabilistic statements about it, because I don't know what the shape of the underlying distribution is. If I additionally tell you that it's normal or binomial, then you can start making probabilistic inferences about those point statistics. Okay? So next class, we're going to start getting into that.